This is section 6.4 Exponential Growth and Decay. We're going to start with separable differential equations. In example 1, it says solving by separation of variables. So that's exactly what we've been doing. So we're going to solve for y. This is the derivative, and we're going to back up to y equals. And we're going to do that by separating the variables. So the first thing we're going to do is multiply both sides of the equation by dx. And we can make that x squared y squared, and we have dx. So we've multiplied both sides by dx, and we have raised both x and y to the second power. Now we want to separate the variables. We want the y squared on the dy side, and we want all the x's on the dx side. So we need to divide both sides by y squared. So we have 1 over y squared dy equals x squared dx. Now we just want y equals, so we're going to integrate both sides. And let's see, this is actually y to the negative 2, so if we add 1 to that, we get y to the negative 1, but if we took the derivative, we'd have a negative in front, so we want to cancel that out with a negative. So we have negative 1 over y equals 1/3 x to the third plus c. As soon as we take the antiderivative, we want to plug in y equals 1 and x equals 1 to find out what c is. So we want to use this initial value. So we have negative 1, that's 1 over 1, equals, well, 1 to the third is 1, so we have 1/3 plus c, and we need to minus 1/3 from both sides. So that's negative 3/3 minus another third, so c equals negative 4/3. Now, so we have negative 1 over y equals 1/3 x to the third minus 4/3. Now, I want to get y by itself. In order to do that, I want to get the right side to be a fraction. So we have just one big fraction. So we have a common denominator here, so I can write this as x to the third minus 4 over 3. Now I can take the inverse of both sides. We could multiply by y, multiply by 3, and then divide. And essentially we're just taking the inverse of both sides. So we have negative y equals 3 over x to the third minus 4, and then multiply both sides by a negative. So the final answer is y equals negative 3 over x to the third minus 4. Exponential growth and decay. Change in the presence of a substance is proportional to the amount present. So we have a proportion, directly proportional. As one increases, the other increases. So the change in the presence of a substance is proportional to the amount present, which means that, well, take the population of bacteria like we have here. The more bacteria in the more bacteria in the dish, the faster they multiply. The more radioactive material present, the faster it decays. The greater your bank account, the faster the greater your bank account, what does that say? Assuming it earns compound interest, the faster it grows. So just saying the more population you have, the more it's going to grow because there's more to populate. Well, it's directly proportional, so the change in the population is equal to k times y. If your bank account gives you 100% interest per year, your rate of growth would be dy over dt equals 2y. It would be doubling. Your account would double every year, and y represents what is in your account. So we're going to solve this equation right here and just kind of see what we get. So we're going to multiply both sides by dt. We're not going to integrate yet because I want to get y with dy, and I'm going to keep the constant with the dt. So we have 1 over y dy equals k dt. Oh, that's not the scroll bar. Well, now we can integrate. And we have the natural log of the absolute value of y equals kt and then plus c. Well, now we want to get y by itself. We want to solve for y. I want y equals. So we need to change the log form to exponential. So we have y equals e to the kt plus c. Well, I can split this into y equals e to the kt times e to the c. Now think about what happens when you multiply these two together. You add the exponents, so we can split this up into multiplication. Well, e to the c is just c, so I can write this as y equals c e to the kt. Now, this should look familiar. In banking, we have the amount in the bank equals the initial amount. Well, I guess they write it as P. So let's do this. P e to the RT, the PERT formula. This is exponential growth with a bank, or it could be exponential decay if K is negative. So if you're given the formula where something is growing proportional to how much is present, then it becomes the PERT formula, or the exponential growth function. It says find the solution of the differential equation where the rate of y is proportional to how much is present. K is a constant that satisfies the given condition. So we can write, since we know this right here, this is what's happening, then the equation, the solution, is y equals c e to the kt. Well, if we plug 200 in for y and 0 in for t, k times 0, we get e to the 0, which is 1, so c is just 200. Now that's the initial value. C is always the initial value in exponential growth with this formula here. So if you're ever given a t value of 0, you can just plug the 200 or whatever is here in for c. So right now we have y equals 200 e to the kt. Now k is, you're told, is negative 0.5, so we have y equals 200 e to the negative 0.5 t, and that's the solution of the differential equation with these given characteristics. We're going to look at continuously compounded interest problems, and when compound interest is continuous, we use the PERT formula. So sometimes we see this as P naught e to the RT. And interest compounded quarterly, monthly, daily, weekly, hourly is the initial amount times 1 plus r over k to the kt, where k is going to be 4 if it's quarterly, 12 if it's monthly, 365 if it's daily, and so on. Suppose you deposit $800 in an account that pays 6.3% annual interest. How much, it's a little too wide, how much will you have 8 years later if the interest is compounded continuously, compounded quarterly? So let's do the continuous. We have a amount after 8 years equals, here's the original amount deposited, 800 e to the k is really the rate, so 0.063, and the time is 8, of course, 8 years. So we're going to grab our calculator and we're going to get this figured out. So we have 800 times e to the 0.063 times 8, which ends up being $1,324.26. 1324 and 26 cents. Now compounded quarterly, we have the amount after 8 years equals 800 times 1 plus the rate is 0.063 over quarterly is 4 raised to the 4 times 8. Now we just have to be able to put this in our calculator correctly. So we have 800 times 1 plus 0.063 divided by 4 raised to the, and then we'll just make that raised to the 32. So $1,319.07. $1,319.07 is the answer for these. $sign there, $sign there, so we have our labels. If $3,000 is deposited in a bank account giving 3.4% interest, find the time it would take for the amount to double if the interest is compounded continuously. So compounded continuously formula is P of t equals P sub 0, e to the RT, and there's other variables we can use. E is going to stay the same, of course. Sometimes we see A e to the KT, but this is the one we use for money. Well, if we're going to double the initial investment, we want it to equal 2 times P sub 0 equals P sub 0, e to the 0.034 t. Well, the initial investment is $3,000, so we want 6,000 equal to 3,000 e to the 0.034 t. Well, when you divide by 3,000, you just get 2 equals e to the 0.034 t. So if it's double or triple or quadruple, this will just be 2, 3, or 4, and that takes care of the initial investment. So now we want the natural log of both sides, and we take the natural log of e to the 0.034 t. You just get 0.034 t because that's inverse operations. So t equals the natural log of 2 over 0.034. So let's grab the calculator and let's get that answer. Let's clear all this. We have the natural log of 2 divided by 0.034. Oop. I don't need that right there. Let's delete that. And we get 20.387. 20.387, and I solve for t, so that is years. It's going to take about 20 years to double the money. A colony of bacteria is grown under ideal conditions in a laboratory so that the population increases exponentially with time. At the end of 4 years, there are 6,000 bacteria, and at the end of 7 years, there are 24,000 bacteria. How many bacteria were present initially? So we're using exponential growth, so we have P of t equals the initial amount e to the kt. Well, they give us 2 points, and it's time, comma, population. So at the end of 4 years, there are 6,000, and at the end of 7 years, there are 24,000. So we're going to plug in the first point. So we have 6,000 equals P naught e to the k times 4, and we have 24,000 equals P naught e to the k times 7. Well, it's okay to subtract equations and add equations, and you can divide equations. So if I take the first equation divided by this second equation, I want to do that because I don't want to work with fractions. I want to work with nice whole numbers. If we take 24,000 divided by 6,000, we get 4. And if we take P naught divided by P naught, those cancel each other out. And e to the k7 divided by e to the k4 is e to the 7k minus 4k. So 4 equals e to the 3k. When you divide, you subtract the powers. So we're going to take the natural log of both sides. Now natural log and e are inverse operations, so we get just 3k. So the natural log of 4 equals, or divided by 3, is going to be the k. So let's get an approximation for k. So we have natural log of 4 divided by 3, enter, so about 0.462. So k equals 0.462. So right now we have P of t equals P naught e to the 0.462 t. Well, now we just have to pick one of these points. We found the k. Now we can pick one of these points to find out what the t is. So we have 6,000 equals P naught e to the 0.462 times 4. Well, I really don't want you guys to use 0.462. I don't want you to use the rounded answer. I want you to use the answer that's in your calculator. And of course, you can write down a rounded answer, but don't use this one. So we can take this times 4, and there's e to the 1.848. So we have 6,000 divided by e to the whatever that value was, 1.848 equals P naught. So now we can take 6,000 divided by e to the answer, and we never did actually use a rounded answer. So the original amount was 944.941. So the original amount is bacteria. The last problem is Newton's law of cooling, and here's the equation right here. It says the temperature minus the surrounding temperature equals the initial temperature minus the surrounding temperature times e to the negative kt. T sub s is surrounding temperature and T sub 0 is the initial temperature. Here's an example. A hard-boiled egg at 98 degrees Celsius is put in a pan under running 18 degrees Celsius water to cool. After 5 minutes, the egg's temperature is found to be 38 degrees Celsius. How much longer will it take the egg to reach 20 degrees Celsius? So hard-boiled egg. So the initial temperature equals 98. The surrounding temperature is the running water that we're putting the egg under. That's equals the 18. We have this point, and the points are the little t, the time, comma, the temperature of the object. So after 5 minutes, the temperature is found to be 38, and we want to know how long will it take to reach 20 degrees. So we have some missing values here. We really have to find the k, and then we can actually solve the problem. So to find the k, we're going to use this point right here. We have 38, which is the temperature, minus the surrounding temperature, which is 18 degrees, equals the initial temperature, which is 98, minus the surrounding temperature, which is 18. And then we have e to the negative k times, and this took 5 minutes to reach a temperature of 38. So we have 20 equals, that's going to be 80 e to the negative 5k. So we have 1/4 equals, because divide by 80, that's 1/4, e to the negative 5k. Take the natural log of both sides, negative 5k. So I need the k is natural log of 1/4 over 5. Now, I'll write down the rounded answer, but of course, we want to avoid using as many rounded answers, or no rounded answers if we can help it. So we have natural log of 1/4 divided by 5. Enter. So negative 0.277. Oh, and if I divide by negative 5 instead of 5, that will give me a positive answer for k, but it's still a negative 0.277 when I plug it in. So now we have a value for k. Well, we're going to use k to predict the temperature or the time to reach 20 degrees. So we have, in this case, 20. Now that's the temperature that we're looking at. That's T, minus the surrounding temperature, which is 18, equals the surrounding the initial temperature, which is 98, minus the surrounding, which is 18, and then e to the, let me slide this over a little bit. I got a little bit of room here. E to the, let's see, what was the value? The value is 0.277 approximately, negative 0.277, and we're trying to find the time that it takes to reach 20 degrees. So we have 2 equals 80, e to the negative 0.277 t. So we're going to divide by 80. So we have 1/40th equals e to the negative 0.277 t. Take the natural log of both sides, negative 0.277 t, and then divide by negative 0.277. And that'll get me what t is. So t equals, let's use our calculator now, we have the natural log of 1 divided by 40, and I have the entire decimal value in the calculator right now, so I'm going to divide by the answer. So even though I've written an approximation down, I'm using much more than just 3 decimal places. So the answer is 13.305. 13.305 minutes, but that's not the answer to the problem, because it said how much longer. It didn't say how long. It said how much longer than the original 5 minutes. So we have to minus 5 minutes off of that. And so the answer they want is 8 point, let's see, that'd be 0, 0, yeah, that'd be 8.305